This is a video for AQA Mechanics, Dimension Analysis, Section 1.2, where we're looking at dimensional consistency of equations. In the first video we introduced the three fundamental dimensions of quantities: mass, length and time. And we can use these to check whether possible equations are going to be correct or not, looking at the dimensions of equations. So for adding or subtracting or trying to equate different parts of equations, then they must have exactly the same dimensions. In other words, we can't add an area to a velocity. So each part of an equation must have exactly the same dimensions. And this is what we refer to as being dimensional consistent. So if we look at this particular equation, we've got volume on the left hand side and then two parts to the equation on the right hand side, then we can decide whether this is a possibility by looking at the dimensions of each part. Well, we know that the dimensions of volume are length cubed, and so if we look at the first part of the right hand side, 1/3 pi r squared h, well, 1/3 and pi are both constants, so they are dimensionless. So we've got r squared, that's a radius squared, so length squared, and h is a length, so that's length multiplied by length, in other words L cubed. So yes, that has the same dimensions of volume. But if we then consider the 2 pi r, then this time the dimensions of that are simply L. So we've got an inconsistency here. One part or two parts of the equation have got dimensions L cubed, but the third part dimensions just L. So therefore that formula can't possibly be correct. So just take a little bit of time to consider these and decide for yourself which of these you think are correct. If you wish, pause the video and then come back to it to check through the results. Well, in the first one, the left hand side has dimensions of force multiplied by distance, so the dimensions of F multiplied by D, or force, is mlt to the minus 2, and distance is L, so we've got ml squared t to the minus 2. On the right hand side we've got a mass multiplied by velocity, so mv and mu are both the same because v is a velocity and so is u, so we've got mass multiplied by velocity here, and velocity is length t to the minus 1. So there we've got ml t to the minus 1. So that's inconsistent, and therefore that formula can't be correct. If we look at the second one, the dimensions of force multiplied by time, well, that must be mlt to the minus 3. I beg your pardon, mlt to the minus 2 multiplied by t, which is mlt to the minus 1. And that's the same as we've just calculated for m multiplied by velocity, so that one is dimensionally correct. And finally, F multiplied by D we knew was ml squared t to the minus 2. And on the right hand side we've got mv squared, so the dimensions of mv squared this time is mass and then velocity, length t to the minus 1, all squared, which is ml squared t to the minus 2. So again, these are dimensionally correct. Now you'd probably recognize that the force multiplied by time is an impulse, so this is impulse is change in momentum is the second one, and then the third one is the equation for work done is change in kinetic energy. So we've just checked that those equations that we've met before do have the correct dimensions. That's the end of this short video on dimensional consistency. In the next video we'll be looking at how we can determine the powers or indices in formulae that we might think are going to be applicable to any particular situation that we have.